Oh, hi. Yeah, hello everyone. Yeah, welcome to today's webinar. So we're so happy to have you here, and we can together we can go over what our thinking about this, how computational storage could possibly play a key role in today's security first environment. So yeah, my name is Tong Zhang. I'm a co-founder and chief scientist at ScaleFlux. So yeah, so let's start today's journey. So let me bring up this slide. Okay, so yeah, again, the topic of today's webinar is really about how possibly the computational storage drive could play a role in today and the future's security first kind of computing infrastructure. So total we have about 30 minutes. So the webinar, this presentation will take about 15 to 20 minutes, and then we will leave about 10 minutes, 10 to 15 minutes for Q&A. So please ask any kind of questions they want when we have kind of some more discussions and the dialogue. Okay, so now let's start. But we all know that kind of data security has become one of the most important considerations in modern computing infrastructure. So it is quite common for the host, the CPU and the DPU to encrypt all the data before shipping them to storage devices and servers. And meanwhile, as we all know that as a topic of current interest, computational storage drive naturally tend to demand a plain text input. So which clearly kind of a conflict with the host side data, like data encryption. So this clearly leads to a very well justified doubt on the viability of a computational storage drive in this security first computing environment. So today, I would like to argue that contrary to this common conception, that is, computational storage drive has no place in this security first environment. It's actually, we tend to argue that the computational storage drive still could play a big role here, even though all the data being shipped to the drive have been already encrypted by the host, the CPU or DPU. So now first, we see a clear trend that modern CPU, DPU are starting to integrate hardware compression accelerators. So this naturally enables the future computing infrastructure to exploit the data compressibility to reduce the storage costs and the network traffic without sacrificing the data security. So here, the most convenient option is to implement compression and encryption on the per 4K byte basis in the I/O stack, completely transparent to the upper level OS and the user applications. So, but however, just due to this unpredictable data block compression ratio, the one big problem here is that how to effectively manage all the variable length data blocks. The most straightforward option is to use the well-known log structured data store to tightly pack all those variable length compressed and encrypted data blocks over the storage device LBA space. So, however, during the runtime, the data update will gradually introduce more and more garbage in the log. So as a result, the system has to periodically carry out the garbage collection. This, as we all know, could dramatically damage or degrade the storage system performance and reduce the kind of SSD lifetime. So how to mitigate such an overhead and penalty? The most convenient option actually is to offload the variable length data management task from the host CPU, DPU into the SSD. And we all know that SSD internally use the data remapping layer, we call the flash translation layer, to manage the data storage over all the non-flash memory chips inside the drive. The FTL inside today's SSD only handles the fixed length 4K byte data block storage management. That like they only handle like the placement of every 4K byte data blocks sent from the host. So very intuitively, like if we could somehow enhance the SSD FTL to handle the variable length data blocks, then it will make it completely possible to offload the host side storage management task into the drive. And also, meanwhile, we all know that as a key storage service, snapshot enhance the system data reliability and safety, but also at the same time induce the penalty of storage cost because we have to store multiple versions of multiple snapshot versions. And very intuitively, like those different snapshot versions of the same LBA data block tend to have a high degree of content similarity, especially under pretty frequent snapshot configurations. So this could lead to what we call the cross snapshot or cross snapshot versions data content redundancy. And it is interesting to realize that even after the compression and the encryption, such data content redundancy still could remain. For example, for one LBA block, upon its snapshot version number 1, if we generate another version of the snapshot caused by this content modification, and then even after the compression and the encryption, and due to the use of the same encryption key for the same LBA address, and also the sequential processing flow of both compression and the encryption algorithm, those two data blocks, that is after the compression and after the encryption, those are two different snapshot versions, they still could have an identical portion. So clearly that it would be great that if we could exploit such cross snapshot content redundancy to reduce the storage cost, of course, without sacrificing the system performance. So here, like one convenient option to exploit such a cross snapshot version redundancy is to offload those tasks into the SSD. So we can pack multiple snapshot versions of the same LBA block into one 4K byte data block on the drive and then send to the SSD. And internally, the SSD performs the compression on a per 4K byte basis so that we can transparently exploit the cross snapshot content redundancy to reduce the storage cost without asking the host, the CPU and DPU to do anything further. So now we can see, like in summary, as the CPU and the DPU start to integrate hardware compression accelerators, future security-first computing infrastructure could conveniently, readily perform data compression without sacrificing the data security. And So that is what we can easily envision down the going like moving forward. So to most effectively implement such we call the low cost security infrastructure, we need to adequately address these two issues. And as we discussed above, the most convenient solutions and options are to offload those corresponding tasks into the solid state drive. So this, of course, like naturally leads to a new breed of computational storage drive with built-in transparent compression. That is, inside such drive, each 4K byte data block is compressed, and the storage of each variable length data block is managed by its internal elastic FTL. So compared with pretty much all the computational storage drive concept proposed by the academia and also including the industry over the past years, this one clearly has a unique advantage, that is by keeping the per 4K byte compression completely inside the drive is naturally 100% compliant with the existing NVMe protocol and does not demand any special changes as a host side software. So this can dramatically lower the barrier and improve its commercial viability and the practical value. So then as shown here, that without any change to the NVMe 4K byte IO interface, such computational storage drives internally compress every 4K byte data block and employs an we call the elastic FTL to manage the variable length data blocks. So to offload the variable length data block management in this low-cost, secure infrastructure from the host CPU and DPU into the CSDs, actually we can use a very simple idea. That is, we could bloat at the host side after the compression and the encryption. We could bloat each compressed and the encrypted data block into 4K byte through this zero padding, and then we can just store the bloated 4K byte block into SSD through the standard NVMe IO interface. And inside the drive, of course, like all the zeros will naturally be compressed away, and then we can maintain the storage cost reduction. So upon receiving those variable length compressed and encrypted data blocks from the host CPU, the IO stack simply bloats each data block and stores them into the CSDs through the standard NVMe interface. Of course, here using such a simple practice we may encounter a potential issue that is like as the data compression ratio increase, then if we bloat every individual compressed and encrypted data block, and then the CSD must expand this LBA space with a larger factor, and a larger LBA space of the CSD will demand a larger FTL mapping table inside the drive. So a larger FTL mapping table will demand more DRAM. But this conflict with the limited DRAM capacity inside the drive. So to mitigate this intra-CSD DRAM capacity constraint, the host can play a simple trick we call the adaptive data block fusion. The basic idea, again, is very simple. That is based on the runtime data access characteristics. We can categorize data blocks as either write hot or write cold. And each write hot data block entirely occupies one 4K byte LBA on CSD, just a simple like a bloating. And at the same time, for the write code blocks, we allow multiple write code blocks to share one 4K byte block on the CSD. Then, as shown here, like among all the compressed and encrypted data blocks, suppose the block A, B, E are write code, and the block D is write hot, and then we will pack blocks A, B, E together into one LBA and leave the block D on one LBA. So then in this way, we will reduce the demand on the CSD LBA space expansion and to better accommodate the limited DRAM DRAM capacity. And at the same time, we minimize this kind of a garbage collection overhead on this. So of course that the host must become responsible for managing the block fusion using the data structures like a B tree. It's a very well started topic. So then meanwhile, actually using this kind of data structure for the management, actually it will also seamlessly support the snapshot fusion, as we discussed before, pack multiple snapshot versions into the same 4K byte block on the CSD drive, so that the CSD drive can naturally seamlessly exploit the cross snapshot data content redundancy to transparently reduce the storage cost for the storage for the snapshot service, and without sacrificing the data security. Okay, so actually upon such low cost secure infrastructure assisted by the computational storage drive with built-in transparent compression, and if we are willing to move one step further to touch and modify upper level OS and user applications, there is actually that huge spectrum to explore further innovations to leverage to better leverage the infrastructure level secure data compression. Along this direction, actually over the recent years, we have done some research to demonstrate, to really kind of demonstrate the potential in the context of B-tree and cloud native database RAID and the key value store. And certainly there are still a lot of more to be do here. Okay, so in conclusion, that is today, we make the case that computational storage drive could still play a key role in today and the future's security first computing infrastructure. So in particular, with increasingly available compression hardware accelerators inside the CPU and the DPU, future computing infrastructure could conveniently integrate secure data compression to reduce the cost without sacrificing the data security. And we have shown that for such low cost security first infrastructure, the computational storage drive with built-in transparent compression could be deployed to largely improve its implementation efficiency and further reduce the storage cost. So upon such an infrastructure, much more could be done to enhance different applications to take full advantage of the infrastructure level secure data compression. But yet, I think today we just scrap the surface of the full potential here. So again, that at ScaleFlux, we very much look forward to working with the whole industry on this exciting journey. So yeah, this ends today's talk. So yeah, thank you very much, and I would be very happy to answer any questions. Okay, yeah. So for the first question, like why compress on the 4K byte chunk. So actually that is the we focus on the per 4K byte compression for a couple reasons. For the first reason, it can be seamlessly integrated into today's infrastructure, like by keeping everything on the once we compress by 4K byte, then we keep everything inside the I/O stack being completely transparent to the upper level OS and the user applications, and so then we don't need to make any change to the upper level. And also by keeping the compression granularity as a 4K byte, we can maintain the random storage system random IOPS. But for example, like if we compress on the 8K byte or 16K byte, then any kind of random 4K byte write will introduce write amplification, and also like any random 4K byte read will cause read amplification. So that will induce very noticeable storage system performance degradation. So for those reasons, we just focus on the keeping the compression on the 4K byte granularity. Yeah, this is a very good question. Okay, so to the slide 9, to saving bandwidth. So for the slide 9, so Laura, could you we go back to the slide? So on the slide 9 here. Oh, okay, I see here. Okay, so I think the question is really kind of because we naturally by compressing the data, we can not only reduce the storage cost, but also we can reduce the network traffic. But here, if we bloat each those data blocks, and before we send it to the drive, then looks like we are not saving the network traffic. So actually, that is a very good question. So so here, like the data, the zero padding or the bloat can be done anywhere. So actually, like if we're talking about like a remote storage, like the host, the compute server compressed and encrypt those different each 4K byte data block, and then actually we don't need the compute server to do the bloating. The compute server can just transfer the compressed and the encrypted data to the remote storage server without bloating, without zero padding. Upon receiving the compressed and the received data blocks, the storage server on its own can just bloat, and by doing the zero padding to bloat the data block, and then send the bloated data blocks to the local SSD inside the storage server. But of course, that will still consume more like a PCIe bandwidth inside the storage server. But fortunately, the PCIe has way more like enough bandwidth than than the SSD. Like the upcoming like PCIe Gen 6 and PCIe Gen 7 will have very abundant PCIe bandwidth. So then that shouldn't be a problem. Yeah. So that is this is a very good question. Okay. So how is a 4K byte piece handled when compression is performed using the CPU today? Yeah, so actually to my understanding, in today's computing infrastructure, the system do not do this fine-grained 4K byte compression at all. For example, like for Amazon, like AWS, for the EBS storage service, I don't believe the EBS when the EC2 server send the data blocks to the EBS node, I don't believe they are doing the 4K byte compression. simply because the management problem. Because really the difficulty of doing the data compression not only comes from the compressing data itself, but also comes from how we can manage the variable length data blocks, how we can manage the unpredictable data compression. The finer granularity we go on the compression, the harder, the more metadata we have to handle when we manage those variable data blocks. Then the harder we handle the variable length like data management. Then back to our example for the EBS, because EBS is a random IOPS oriented. So then we have to guarantee very high random 4K byte read, 4K byte IOPS, random 4K byte IOPS. So as a result, if we want to use the compression to reduce the EBS storage cost and to reduce the network traffic between the EC2 server and the EBS node, we have to compress on the per 4K byte basis. However, for this per 4K byte compression, it will be a nightmare for the EC2 server to directly manage those variable lengths, those huge amount of compressed 4K byte blocks. So that will be a big headache, big nightmare. And then that could, even though we could use the hardware accelerator to accelerate the compression, but if we ask the CPU and DPU to be responsible for managing those variable length 4K byte, like variable length compressed blocks, that could largely hurt the performance. And that is where the computational storage drive with built-in transparent compression can come in to greatly relieve the host, the CPU and the DPU from doing this kind of management task. So that is why we believe that even for this encrypt everything environment, the computational storage drive still could play a big role. Yeah, it's a very good question. Yeah. What happens on the read side? So yes, on the read side, then automatically the drive, the computational storage drive will pad the zero again, will resurrect those padded zeros, and then send to the host through the PCIe, and then the PCIe, then the host can just do the decryption and the decompression. Yeah. So and also if this is a remote server, then we can just the storage server can just remove those padded zeros and only send the compressed and encrypted block. Yeah, this is a very good question. Yes, this cross snapshot redundancy is impacted by the use. Yeah, certainly the compression and encryption could degrade the cross snapshot redundancy, and also it depends upon how the snapshot content are modified, and when we apply the compression and encryption across different the snapshot versions, different kind of a modification pattern on the content will result in a different kind of cross snapshot redundancy. Yeah. Okay, so that's already we're at the end of our 30 minutes for this webinar. Again, thank you very much for attending this webinar, and we're if you have any questions or other remaining questions, please feel free to contact us, and also the slides and the video will be posted later on.